Okay, so we're going to continue on and we're going to talk about graphing, and we're going to think about the whole graphing algorithm that we had. You guys can break out the graphing algorithm. What I'm going to do is we're just going to do a really quick example. So imagine that we had to graph the following. Well, let's even make it really easy. So imagine that we had, okay, here we go. So we're going to graph. I want to graph with all details. How about we're going to make it interesting. So how about if we did x squared minus 9 times x plus 4. Now, advantage to that is we can factor it, find the roots really easily. So if we think about this, let's change it from y to make it f of x. Whatever, doesn't matter. So it's going to be x plus 3 times x minus 3 and x plus 4. So if we think about that, we're going to have roots at x equals 3, -3, and -4. And I guess the y-intercept, if I put in x equals 0, it is going to be -4 times -9 times 4 is -36. Okay, so we could be framing this all up, adding those details. So we have those. Lovely. Maybe I'll even do that. Let's get some framing going on here. Yoink and yoink. Okay, how about that? So we're going to have, that's not blue, is it? Or that's probably not blue either. Let's pretend it's blue. -3. And why didn't I space that out? Let's erase that. Do better. Come back here. All right, give me more room. Here we go. -3 and -4. And 3. About the same distance over here. 3. And then different scale on our x or y-axis. There's my y-intercept, -36. Now, this is a cubic, right? And we know in the grand scheme, it's got a positive leading coefficient. So a cubic is going to look like this. We know that. But nevertheless, we want to demonstrate all of these features appropriately. So we're going to have to find out what f of x is to differentiate it. And I mean, in theory, we could differentiate it from here because we could do product rule. Actually, that actually might not be a bad idea. It'd probably be easier to do that than it would be to expand it. Nevertheless, I'm going to expand it. So f of x is going to be x squared times x is x cubed plus 4x squared minus 9x. X is pretty easy, not minus 36. Okay, there's f of x. So I'm going to take the first derivative. So f prime at x is going to be equal to 3x squared plus 8x minus 9. Now, I didn't cook this at all beyond having some lovely roots. So what I'm going to do here is I know I want to set, so I'm going to let f prime at x equal 0 to find criticals. Right, so we're going to do that. This I'm sure doesn't, well, I'm not sure, but I'm relatively confident it's not going to decompose very nicely. So I'm going to just jump right into quadratic equations. So we know x is equal to -b plus or minus the root of b squared minus 4ac all over 2a. All right, so get myself some more room here. So -8 plus or minus the root of 64 minus 4 times a times c. So minus 4 times, actually make it plus because it's going to be 3 times -9, which makes it plus. All right, 9. All over 2 times a. So all over 2 times 3. Lovely. So simplify that a little bit. Grab my calculator. So under the radical, we're going to have, go away from there, 64 plus 4 times 3 times 9. So the radical, not going to be a nice number, 172. So we're going to have, this is -8 plus or minus the root of 172 over 6. And split that off into two pieces, vert and vert. And I'm going to just kind of get the values. I don't feel like writing it all, taking your time up with that. So grab those values. So we're going to have bracket -8 plus the root of 172, close those brackets off, divided by 6. So the plus branch is going to have 0.85. So I'll call this the plus branch 0.85. And the minus branch is going to have, go up here, change this over to be minus, there we go, negative 3.52. So negative 3.52. So those are eligible to be critical values. Now, in theory, we don't know if they're maxes or mins, but because it's a cubic and we know enough about cubics, we know they're actually max and mins. However, we are still going to do a sign chart for this, okay? Because the sign chart is going to show us areas of increase and areas of decrease, right? So we're going to go like this and like this. If it factored nicely, we'd list the factors. It doesn't factor nicely, but nevertheless, negative 3.52, and this is 0.85. And this goes from negative infinity to negative 3.52. And this goes from negative 3.52 to 0.85. And this goes from 0.85 to infinity. Now, this, if I asked you to graph with all detail, you would need to include this sign chart for the first derivative test, because even though we know the details, that's not really the point. The exercise is just demonstrating the capacity to do these things. So we're list the test values off. So test value, I don't know, like negative 10, 0, and make it interesting of just 1. Now, there are no factors that are nice. So if they were nice factors, I would list them and then use it. But because of that, there are no factors. So it's just going to be whatever the answer of 3x squared plus 8x minus 9 is when I put that in. Now, we can go ahead and we can do that. Or we could say, well, that's going to be negative 10 squared is going to be just 100 times 3 is 300. That's not going to take it away. So that overall is going to end up being positive, which is no surprise because it is a quadratic, and we know quadratic comes, yeah, whatever, you know that. So that means the result is, this is the result, it's positive. And normally we'd have a result row that we would, kind of simplify all that, it's positive. And so because of that, we know that the direction, right, the direction is upwards. It is increasing. Similarly, we put in the 0. It's going to be negative. I can see that. So the result is negative. It means it's going downhill. So what we have found here is we know that this must be a local max, right? Because it's increasing, 0 slope, decreasing. It is a local max. So the local max is at negative 3.52, comma, whatever the value is when I put that into the original function. Similarly, over here, we put in 1. 1 is going to be 3 plus 8 is 11 minus 9 is 2. So it is positive, not surprisingly, it's positive, which is increasing. So clearly, this is going to be a local min. We're going to put that in 0.85, comma, whatever. Okay, and I'm not even going to bother with that, but you would know, you would just take those values, put them in the original function, and get those things. Okay, so our intervals of increase are from negative infinity to negative 3.52 with round brackets on both sides, unioned with 0.85 this, right? So those are our intervals of increase. Interval of decrease is this interval right here. Local max, local min. Lovely. Okay, on we go to our second derivative test. So the second derivative, we have to take that same function. Do I have it up here? And we're going to differentiate it. So 3x squared plus 8x minus 9. I can't see it very easily. So 3x squared plus 8x, was it minus 9? Crap, minus 9. All right, let's get a little minus in here. Minus 9. There it is. So that's f prime at x. So I want f double prime at x. F double prime at x is going to be equal to 6x plus 8. And hey, I'm going to let f double prime at x equal 0 to find eligible POIs. And so we would do that, and we would find out then that x is equal to negative 4/3. Again, I know it's going to be a point of inflection. It has to be because it's a cubic, and I know enough about cubics that it's going to be, but I would still need to test this. Okay, so here we go. So we're going to test our concavities here, right? So this is going to be negative 4/3. Oh, stop that. Better. Negative 4/3. Now, what's important to know is that if this was anything, well, that's from negative infinity. Sorry, got distracted. That's not infinity. Whoa, baby. So if this had any asymptotes, vertical asymptotes, not only would we put our critical values up here and our eligible POIs here, we would need our vertical asymptotes in there as well in both of these positions, right? Because if we think about what we're checking for where it's increasing and decreasing. Well, increasing and decreasing can change on either side of a vertical asymptote. Similarly, concavity can change on either side of a vertical asymptote. So we would need to include those if this were a more complex example, but it's not. And then from -4/3 to infinity. Test values, plunk them in. And so we're going to put them into that. So I can actually list the 6x. Wow, 6. Ooh, maybe it's late. 6x plus 8. We would test our value, I don't know, -10, and that's going to end up being negative. And we're going to test a value of 0, and that's going to end up being positive. So this is, we're going to talk about shape, right? That's what this test is for concavity. Negative, that makes me sad. Sad. And positive, yay team, it's sunny out. There we go. Okay. And so because the concavity changed on either side, we know that we have a point of inflection. The point of inflection is, of course, at -4/3 and whatever it is when I put that back into the original function. So we could take all of those details and we could drop them into this graph. And because it's a cubic, I already know what it basically has to look like. It has to go like this, and I would have found that point by now. Where was the? It was at 0.85. So this is not going to be a pretty graph. Whatever. Vert goes like that. Whoa. Anyway, something like that. And this would be 0.85. And this one would be, the x coordinate would be -0 or -3.52. Right? And we'd have that ordered pair. And we also know that we have a point of inflection. The point of inflection we found was at -1 1/3. And so you can tell that the concavity, because it's just a graph of absolute beauty, there's my point of inflection at -1.333 repeated, right? There it is right there, the 18. Okay, so look at your graphing algorithm, visit all those things. Recall, of course, that we have to frame up the curve. We have to find the intercepts. We have to do the first derivative test, we have to do the second derivative test, and then we have to add all those things. At the end, we also need to state domain and range. Now, this is dead easy. So the domain for this particular one is simply x a member of the reals. And then the range for this one is, of course, y a member of the reals. And there we go. Lovely. Awesome.